today's class buffer solution. After that we will go to HS equation, that is Henderson-Hasselbalch equation. So we will see in buffer solution, types of buffer solutions: acidic buffer, basic buffers. Example for acidic and basic buffers. Then when you are adding 1 drop of acid or base, what is going to happen, but how it will buffering capacity happens in the buffer solution. So we have seen up to this. So here you see that the pH of buffer slightly comes down to 4.66, not more than that. So the variation in the pH will be between this point to this point. It is 4.83 maximum, 4.66 minimum. So at the center only you have 4.74. So that only this variation in the graph is shown here. That is because of buffering action of this buffer solution. So even though you are adding 1 drop of acid or base, the pH will never change drastically. It will change within this range only. In the graph, it is shown in the graph. So that is why it is called a buffer. That is the main function of a buffer solution. So now, if you say what is a buffer, the buffers are the compounds or the mixtures of compounds that by their presence in the solution, they definitely resist changes in pH. We have seen in the previous graph. They resist changes in the pH upon the addition of a small quantities, that is 1 or 2 drops, small quantities. First one is 1 sodium, potassium is there, K. Another one is K2. 2 potassium is there. That is why it is monobasic potassium, dibasic potassium. So 2 components are there. That is a solution of a definite pH. That is its pH is already known. It's having a definite pH. Be prepared and stored. It is already prepared and stored in the laboratory. Its pH is definitely known. The preservation of such a solution in the laboratory is even more difficult than its preparation, because you are preparing very easily, but you are going to store it in the lab for a long period. See that it should not be changing its pH, because you are going to store it for a long period. But even after that, the pH should not change. If solution comes in contact with air, because you have to properly preserve it. Suppose you have keep it open, it will come contact with air. It will absorb carbon dioxide from the air and it becomes acidic. On the other hand, if the solution is stored in a glass bottle, alkaline impurities from the glass, suppose sometimes alkaline impurities are in that bottle, glass bottle, they may alter its pH. So pH is changed. So due to all these reasons, pharmaceutical solutions are buffered as the buffer solutions. That is why they are using buffer solution. Because if you are keeping the content in a buffer solution, the buffer will not change its pH at any cost. So that is why pharmaceutical solutions are buffered as the buffer solutions that are capable of maintaining pH at some fairly constant value when even small amounts of acid or base are added. So that is the function of the buffer system. That is why buffer system is needed. Necessity comes here. Then applications of buffers. Applications of buffers are used in various fields. First one, in biological system, that is in our living system, in our body. What is the use of these buffers in our biological systems? The pH of blood is maintained. We know that it is about what is the pH of the blood, 7.4. So the pH of the blood is maintained at about 7.4 by two buffer systems that is already there in our body. It's a natural buffer system which is present in our body. One is primary buffers. These are present in our blood plasma. This plasma contains two primary buffer systems: carbonic acid, carbonate, sodium carbonate, carbonic acid buffer system, and acid alkali, sodium salt of phosphoric acid buffer system. So two buffer systems are there in our blood plasma. Secondary buffers these are present in erythrocytes. That is in order to adjust the pH of the product to that required for maximum stability, because maximum they have to store for a long period without change in the pH. So for that buffer systems are used. In parenteral preparations, that is in injections, that is you are having a drug which is injected through injections. So in that buffers are used. In case of that is parenteral of preparations, pH should be considered carefully, as large deviations of the pH may lead to serious consequences when you inject it. So the ideal pH of a parenteral product is 7.4. Why it is 7.4? It is our blood pH, which is the pH of our blood. So the most commonly used buffers in parenteral products, that is injections. They are all acetate buffers, phosphate buffers, citrate buffer, glutamate buffers. So they are all used here in pharmaceutical industry. Then in ophthalmic preparations, that is eye preparations, eye solutions, that also buffers are used. Buffers are generally used in ophthalmic preparations to maintain the pH within the physiological pH range of lacrimal fluid. The fluid which is secreted by eye is called lacrimal fluid, eye fluid. So the lacrimal fluid has a pH in the range of 7 to 8, that is near neutral, that is near blood pH, but it has good buffering capacity and it can tolerate preparations having pH values between 3.5 to 10.5 with little discomfort. So outside this range, that is outside this 3.5 to between 3.5 to 10.5, it increases lacrimation. Lacrimation means you will be crying. Eye liquid will come out. That's called lacrimation. That may occur with other complications. So the buffering agents most commonly used in ophthalmic preparations include borate buffer, carbonate buffer, and phosphate buffers. In ointments and creams, creams what we are using on our face. So topical products which are used on our skins, such as ointments and creams, they are also buffered. They are also kept in buffers to ensure stability of the formulation. The most commonly used buffers in ointments and creams are citric acid and its salts, citric acid buffer, phosphoric acid and its salts, phosphoric acid buffer. So this is about buffer system. Now we are coming to HS equation. What is HS equation? Derivation of the buffer solution. We can use this HS equation. It's widely used to calculate the isoelectric point of this HS equation. Lawrence Joseph Henderson, he wrote an equation in the year 1908. Using that equation, he described the use of carbonic acid as a buffer solution that is there already in our body, biological system. The next person called Albert Esselstyn, later he re-expressed formula. Henderson wrote a formula, he re-expressed that formula in logarithmic terms, logarithmic values, resulting in a new equation. So the equation is called Henderson-Esselstyn equation, because first Henderson wrote the equation, but Esselstyn re-expressed in logarithmic form. This equation is called Henderson-Esselstyn equation, HS equation. Esselstyn was using the formula to study the metabolic acidosis in our body. Now we can see the derivation of HS equation. For example, take this reaction. HA plus H2O water. The water interacts with HA. You'll get H3O plus. One proton is added with that HA, so that it becomes H3O. Yes. So this HA is a weak acid. So composition of an acid, this weak acid, can be described by an equilibrium expression like this. So this HA dissociates in presence of water, it will become O plus A minus. Consider the case of acetic acid. Suppose you are taking this HA as acetic acid. So this acetic acid is weak acid. So instead of HA, you take the CH3COH. And the acetate anion for this acetic acid A minus is CH3COO minus. So write the equation. CH3COOH, that is HA plus water, it gives CH3COO minus plus H3O plus. This H3O plus and this is CH3COO minus. So this is the reaction. So now take this reaction and calculate Ka. Acetate is the conjugate base of acetic acid. That is CH3COO minus. That's called acetate. It is the conjugate base of acetic acid. Acetic acid and acetate both are a conjugate acid and base pairs. So we can describe this relationship of these two with an equilibrium constant that is called Ka. If you want to calculate the equilibrium constant Ka for this acetic acid, that is called Ka. Ka the formula is H3O plus. This is the product of that reaction. The molar concentration of H3O plus, that is why we have written in this bracket. Then into molar concentration of A minus. A minus is acetate divided by molar concentration of the acid HA. This is the formula to calculate Ka. So apply this formula for this acetic acid. Taking the negative log. So you are taking logarithmic value, negative log on both the sides of this equation. So taking the negative log of both the sides of the equation, it gives minus log Ka is equal to minus log H3O plus molar concentration into A minus molar concentration divided by HA. Or I am rewriting this equation, minus log Ka is equal to, minus log Ka, I am going to rewrite it as pKa. This minus log H3O plus, I am going to rewrite this as pH. Because you know that pH is my negative logarithm of H plus ion. So this is pH. So this is minus log Ka is pKa. pKa is equal to pH minus plus in the previous equation. I am going to use the symbol minus so that it will be reverted. Minus A minus delta by HA. So this equation can then be rearranged to give HS equation. So pH is equal to pKa plus, I am removing this minus and instead of that I am using the symbol plus. So pH is equal to pKa plus log of negative to plus when comes to be rewriting. So pKa is plus log A plus divided by HA. That is equal to pKa plus log of conjugate base. It is called conjugate base divided by the acid. So now I am going to write the Henderson equation for an acid. So pH is equal to pKa plus log A minus by HA. Here pKa is equal to minus log Ka, where Ka is nothing but the acid dissociation constant for this acid. That is pKa is equal to minus log H3O minus by HA. For the non-specific acid-based reaction, acid is equal to plus water, and that is conjugate base. You get conjugate plus H3O plus. So this is the Henderson equation for an acid. So now the Anderson-Weisbach equation for a base, that is POH for a base. So POH is equal to PKB. KB is for base plus log, it is BH plus divided by B. B is a base, where BH plus denotes the conjugate acid of the corresponding base B. So you see the reaction for this base B plus H. This is a conjugate acid gives BH plus OH minus. So estimating blood pH. For estimating blood pH, this Anderson equation is used. So a modified version of the HS equation can be used to relate the pH of blood in our blood to constituents of the bicarbonate buffer system, because the bicarbonate buffer system is there in our blood. So pH is equal to pKa of CO3, that is H2CO3, that is carbonic acid. So pKa of carbonic acid plus log HCO3 bicarbonate, CO3 minus by carbonic acid CO3. So where minus pKa of carbonic acid is the acid dissociation constant of carbonic acid, equal to 6.1. HCO3 is bicarbonate, that is the molar concentration of bicarbonate in the blood. Then H2CO3 is the concentration, that is molar concentration of carbonic acid in the blood. So significance of or importance of HSE. So by this equation, the pH of any buffer solution can be calculated from the initial concentrations of the weak acid and the corresponding salt of that weak acid, provided when Ka is given. The equilibrium constant of the reaction is given. However, this Anderson equation for a base buffer will give POH, and so pH can be calculated as like this. That is by pKa and pKb can be calculated by measuring the pH of a buffer solution that is containing equimolar concentrations of the acid or base and its corresponding acid and the hydrolysis of the base. So the dissociation of water itself is neglected as well. So these approximations will fail in reality when dealing with in a real reaction. So when dealing with relatively strong acids or strong bases.